Well, hello. Today we're going to be discussing exponential functions. We started talking about functions a few weeks ago, and everything else the rest of the semester is function, function, function. Functions assigned to each x value exactly one y value. And today we're going to be looking at a certain type of function called an exponential function. And you can probably guess that these are going to be functions that involve exponents. So the first thing I'm going to do, we're going to state some rules regarding exponents. And the first rule I'm stating a to the 0, I'm defining what we mean by a 0 exponent, equals 1. Anything to the 0 power is 1. That's what that says, with one exception. 0 to the 0 is not 1. It's undefined. Sometimes students don't believe it unless they see it on a calculator. Any number, let's say 5, this little caret top key is how you enter an exponent. There's other than square. There's a square here. There's also a -1 exponent there, that little button. But as anything raised, or 5 to the 0 power is 1. Okay? But, and this I'm just saying, it's just a formality. It's not going to actually pop up anywhere. 0 raised to the 0 power is not defined. Okay? So that's not something that y'all will be doing. Generally, you'll see things that you'll hear anything to the 0 power is 1. Now, problem number 1. Just jumping into the homework. -47. all raised to the 0 power. This is one of those problems where there's not a lot of work to it. -47 to the 0 power. You're using that rule. Anything to the 0 power is 1. So, -47 to the 0 power is 1. If you wanted to punch that into your calculator, make sure you put those parentheses. -47, close parentheses, raised to the 0 power is 1. Okay? The next few problems, we're going to work with negative exponents. So here's a couple more rules. When we're working with exponents, the little thing that's floating up there, that's called an exponent. And do y'all remember what the thing right here is called? It starts with a B. It's a base. Yeah, base and exponents. I used to use B for base when stating these rules, but unfortunately the lowercase b always wound up looking like what number? A 6 maybe, so that's why I'm using A. Hopefully the A doesn't wind up looking like a number. There's two definitions for negative exponents. If you have an integer raised to a negative power, A to the negative n means 1 over A to the n. If you have a fraction raised to a power, to a negative power, A over B to the negative n power, and we're about to do examples illustrating this rule. Oh my gosh, I'm so stupid. There. Oh, let me move this. I'm sorry, I'm here writing the rules and y'all can't even see them. A to the negative n power, a negative exponent means 1 over. So a to the negative n is 1 over a to the n. Then the corresponding rule, the other one that goes with it, is how do you raise a fraction to a negative power? Well, a over b to the negative n is b over a to the n. Okay? You just flip the fraction to get rid of that negative exponent. So if you just have an integer, not a fraction, raised to a negative power, write it as 1 over, and that gets rid of the fraction, the negative exponent. If you have a fraction to a negative power, flip the fraction. Those two rules are the ones, we're going to use those for the next 5 problems. Let's move to problem 2. 1/3 to the negative 2 power. Let's see. You've done it. 1/3 to the negative 2. Oops. 1/3 to the negative 2 power. That would be this rule right here. You have a fraction to a negative power, so just flip the fraction. Flipping the 1 over 3, we'd get 3 over 1, which we could just write as 3. 3 over 1 just means 3. By flipping it, we drop the negative exponent, so we have 3 squared, which is what? 9? So 9, let me type that in. I think yesterday a student wanted me to see, well, if I punched in 9 over 1, would it take it? And it did not. Oh, here's another one. 4/5 to the negative 3rd. 4 over 5 to the negative 3rd power. Oh, and I twisted my ankle the other day. That's why I'm sitting. That's one of those things I didn't need to say when I was recording. I should have paused it to say that, but okay. What I'm trying to show with these red negatives is, what do you do to get rid of that negative exponent? Like on the thing what I'm about to write, there won't be a red there. 5 over 4, Exponent 3. Now don't say 15 over 12. 5 cubed. 5 times 5 times 5. 5 times 5 is 25. 25 times 5 is 125. 4 cubed is not 12. It's 4 times 4 times 4. 64. 4 times 4 is 16. Times 4 is 64. If you doubt it, or if you just want to be certain, punch it into your calculator. Nothing wrong with that. So 125 over 64. Number 4 says, rewrite this without a positive exponent. So this is problem 4. P to the negative 9th power. Let's see. It says rewrite using a positive exponent. Well, we have 2 rules about negative exponents. What to do if it's a fraction to a negative power. That's what we did on problems 2 and 3. But this first rule here, that's the one we're going to use on this one. We don't have a fraction. It's just the variable p to the negative 9. So what am I going to have to write in red to get rid of that negative? 1 over, and then it's just p to the 9th. Okay. It might look to you like I'm just writing the problem down and then writing the answer. And yeah, that's what I am. That's what I'm doing. These first half of the assignment, there's not a lot of writing to get the answer. So let's see. Y'all caught up? 1 over, I'll put a p raised to the 9th power. Okay. You ready for the next one? Oh, look at this one. Here it says, write your answer express using a negative exponent. So on this one, your answer is going to have a negative exponent. So you're basically going backwards from what you did on problem 4. Let's see, we have a 1 over, what is that, a 2 to the 9th? 1 over 2 to the 9th. Let me lift this up a little higher. Exactly. Did you hear that? Oh, I hit it off. Exactly. We're taking this rule and going backwards. If you have a 1 over, what that's saying is if you have a 1 over, to get rid of it, just make the exponent negative. So going backwards, 1 over 2 to the 9th would just be 2 to the negative 9th. 2 to the negative 9th. Once again, if you just look at my sheet of paper, it looks like I've just written the problem down and written the answer. About 4 and 5. There's not a lot of work to it. 2 raised to the negative 9th. Okay. This one's sort of like the one we just finished doing. Except instead of a 2 to the 9th, it's is that a v to the 7th? I think I heard it. It's 1 over v to the 7th. So 1 over v to the 7th is v. How do I rewrite it? Well, to get rid of the 1 over, just make the exponent negative. So v to the negative 7th. V raised to the negative 7th power. Any questions? Because I'm going to give us two more rules of exponents. I wanted to say new rules, but they're not new. There's nothing in this course we do that's new. Okay? But they're new to y'all in that I haven't stated them yet. So here's another rule. Oh wait, yes we did this rule. When we were solving those square root and cube root equations, we told y'all what a fractional exponent means. A 1 over n power is just another way of writing nth root. In other words, a 1/2 exponent is a square root. Ooh, messed up my colors. There. A 1/3 exponent would be the same thing as a cube root. Just to make sure it's clear, a 1/4 exponent would be a 4th root. Dot, dot, dot. Instead of having to just list it forever, we can say a 1/n exponent is an nth root. A 1/10 exponent would be a 10th root, so forth. The natural question to ask is, what if this number on top isn't a 1? And we'll see at least one or two of those in the assignment. Well, that's not hard at all. If the top number is something other than a 1, I'll call it a m. So if you have something other than just a 1 over a number, the bottom number is always the root. The top number is the power. So a to the m over n power, you'd write it like this. It would be the nth root of a, all raised to the m power. Oh, I'm sorry about this. So, if it's fractional exponent, hopefully you see how this rule differs from the other ones. The other one, it was a negative exponent. And you said, well, wait, there's a fraction here. Yeah, but that's not the exponent. The exponent is negative on this second rule. On this third rule, it's the exponents that are the fractions. So, let's see. Problem number, what are we up to? Number 7. It says, rewrite without rational exponents. Rational is just another word for fraction. So rewrite without the fractional exponents and simplify if possible. So let me write the problem down. We have an x raised to the 1/5 power. We're going to write it with one of those little radical symbols. That's what it means when it says rewrite without rational exponents. It says simplify if possible. It won't be possible to simplify here. Here in this part of the instructions it says use radicals as needed. That's that little funny symbol. So x to the 1/5. I guess I sort of stopped too soon. If I'd continued on with this, the red 1/5 exponent, 5th root of x. What we call algebra today was actually developed over centuries with different people around the world setting it up, working on it. In one part of the world, they were using these little symbols, these radical symbols, to denote the roots. And in the other part, like instead of a square root, they were using this little idea of a 1/2 exponent. So you wind up with two different notations that mean the exact same thing. Now to type this in, I'm not sure if we've typed in anything other than square roots so far this semester, but that's what this root is here. This little symbol here, nth root. You first type in the root, 5, then you type in the x. Rewrite without rational exponents and simplify if possible. This one you can probably simplify because there's numbers in it. On problem 7, the way there wasn't a number, it just said X. You couldn't do anything with it. Number 8. 16 to the 1/4 power. 16 to the 1/4 power. Well, the 1/4 exponent is a 4th root. So we have the 4th root of 16. Now don't say 4. This is something we can figure out just by thinking about multiplication. What number could we multiply 4 times to get 16?
What number to the 4th power equals 16? What did you say? No, I think 4 to the 4th. Let's see.
4 times 4 squared would give 16. I think it's smaller. What number could we multiply 4 of to get 16? If I multiplied 4 2's, is that going to give me 16? I think it is. It's sort of like 4 times 4. Oh, wow, that's the stupidest statement I've ever said. It's not sort of like 4 times 4. It's exactly like 4 times 4. So the 4th root of 16 is 2. That's what it means about simplify if possible. Y'all see how I got the 2? I had to think to myself, what number could I multiply 4 of? What number to the 4th power gives 16? So 2. Are y'all caught up? Oh, well, let's see. Let's see. Okay. Let's see. Picking up where we were, number 9. Rewrite without rational exponents and simplify if possible. I bet you we can simplify this. Let's see. Let me write the problem down. It's 256 to the 3/4 power. Let me then switch over to where I'm writing. There. I'll probably want that little calculator in a minute. So, this 4 here, this denominator, hold on, let me make some more room down here. Oh, there. Okay, so, pull it over. Let me adjust this camera so I have more. There, okay. That 4 is the index on the radical. So just like on number 8, we're going to have a 4th root of 256. That's the radicand. And notice our numerator is no longer just a 1 on that fractional exponent. The numerator is a 3. So that 3 is what goes outside of the 4th root of 256. So the 4 says we have a 4th root. That 3, that numerator 3, is the exponent or the power that we put on that 4th root of 256. So the question is, what is the 4th root of 256? You're asking yourself, what number to the 4th power will equal 256? 4, let's see. Okay, let's see. So you're thinking it's 4, so if I go 4 raised to the 4th power, is that going to give me 256? I think it is. So
Basically, yes. Although I'm assuming you're using a calculator for number crunching and stuff, then I bet you have you can probably use your calculator to figure it out. But I would say what it really is just sort of guessing. Okay, say you tried 2. You already knew 2 to the 4th was 16. 3 to the 4th, 3 to the 4th, 3 times 3 times 3 times 3, that's 81. So the next, okay, try going up, and that's how you got the 4 to the 4th for 256. So the 4th root of 256, the 4th root of 256 is a 4, but we still have that 3. We still have this 3 right here sitting outside there. So that's saying 4 cubed. 4 times 4 times 4, 4 times 4 is 16, times another 4, that's going to give us 64. And you can verify it with your calculator. 4 raised to the power of 3, and sure enough, it gives us 64. Any questions there? The important thing is that denominator on that exponent 4. That tells you what sort of a radical you're having. That's a 4th root. That numerator 3 is what you're raising the result to once you've simplified the radical. And let's punch this in. So what did we say it was? 64? Any questions there? Now, if you have your calculators with you, let's look and find your exponent key. Let's find that exponent key, because something like this problem here, you could evaluate it using your calculator with your exponent key. So I'm going to pause this. Well, actually, no, I'm not. I'm going to show you how you would punch it in on this TI-83 Plus I have up here. We want 256. Now, to make sure your calculator is doing what you want it to do, I would enclose the base, 256 in parentheses. 256. Okay, that's the number that's being raised to the power. And then raised to, my exponent key is this upside down V here. That's called a caret top. And now that exponent 3/4, to make sure your calculator is doing what you want it to do, and close the exponent in parentheses also. 3 divided by 4. So 256 raised to the 3/4 power. Yeah. This calculator agrees with the calculations that we did on our own. 64. Okay, is there anyone? Let's see. You have your calculator. Did you get it punched in? I'm going to pause the video. Okay. Picking up with number 10. Simplify 36 to the 3/2 power. Let me write that down here on my paper. Okay, it's number 10. We have 36 to the 3/2 power. And y'all laugh at me as I'm up here saying this stuff out the way I am, writing down the problem. But I'll tell you something, I see the same thing in those test videos. I have students sitting there talking their way through, as they're taking the test, which is exactly what I would be doing if I were taking the test. Let's switch over. Okay, let me move there. Okay, I think I put up a little there. That's better. Remembering the properties of rational exponents here, that my brother had written down. Remember, an exponent of 1/2 is the same thing as a square root. If your denominator on that rational exponent is a 2, then generally we don't show it. So that 2, that says we're going to have a square root. And we don't have to put an index there on that radical. Underneath the radical, we'll have the 36. What are we going to have outside this radical? The 3, that exponent of 3. And the square root of 36, we know what that is. The square root of 36 is 6. And we still need to raise it to the power of 3. 6 cubed, 6 times 6 times 6. 6 times 6 is 36, times another 6 is 216. Any questions on my logic? And once again, if you're using your calculator, 36, right? I guess I should have closed 36 in parentheses, but I forgot to. So that's okay. I can get by without the parentheses around the 36. But I really need the parentheses around that 3 over 2. And it better give us the same answer we just got by doing it by hand. And sure enough, it does. Any questions there? Any questions? Oh, where's the... I don't even see the mouse. Isn't that terrible? Where's the mouse? Oh, I see it now. There's just too much white there, isn't there? There it is. Oh, I thought we were through with these problems. But here's another one. Now they want us to take the radical and write it with the rational exponent. What exponent is the same thing as a square root? Let me write this problem down. The square root of 13. The square root of 13, they want us to write that as 13 to what power? What exponent is the same as a square root? 1 over 2. If we're going backwards, a square root is the same as the exponent of 1/2. So we come over here and we punch in 13, use our exponent hot button, and up there we'll write 3. You could use a little slash. If you use just the slash from your keyboard rather than the fraction hot button, it'll automatically write it as a fraction when they realize it. Wait a minute, it's not 3 over 2. What am I saying? What should I have up here? A 1. Where did I get the 3? I have no idea. Any questions there? Here's another one. They want us to write it with a rational exponent. In this case, let me write the problem down. It's the cube root of 18. The cube root of 18. We know that if it's just a square root, the exponent is 1/2. If it's a cube root, the exponent is... Okay, I agree. A cube root is the same thing as the exponent 1/3. So 18 to the 1/3. I'm forgetting to box my answers in. Yeah, okay. So we come over here and we type in 18 raised to the 1/3. Any questions there? graphing exponential functions. Okay. Before we look at these, I think I'm going to graph one. I'm just going to make up one. Okay. An exponential function, we've been using properties of exponents. An exponential function is a function that contains a function that contains an exponential expression, but the difference is that the variable is located in the exponent position, not as the base. Normally, here's what we've been seeing, right? Normally, we see things like x squared and x cubed, right? With an exponential function, it's a function where the exponent contains the variable. So exponential expressions would look something like, if it's an exponential expression, it would be something like, instead of x cubed, it would be something like 2 to the x, or 5 to the x. Just up with, in terms of exponents, that thing right there, the 2 and the 5, that's called the base. And the stuff that's written up here is called the power or the exponent. We know that terminology. We're going to graph exponential functions first. And then we're going to solve some exponential equations. Let's say graphs of exponential functions. Let's suppose we wanted to graph the following. I'm just going to make up an example. Y equals, I think I'll use this 2 to the x. Y equals 2 to the x. To graph exponential functions, we're just going to make a table of values and plot points. We're not going to do anything real sophisticated, but let's think about this a moment. We have a positive number. A positive number to any power will always have what sign? If your base is positive, a positive number to any power, let me shoot that down. What sign is it going to have? If your base is positive and you put any exponent you want to on it, it's still going to be what sort of number? A positive number? I agree. A positive number to any power, that means every y value is going to be positive. Let's make a table of values. Okay, make myself a table of values. Generally, if you use the integers from 3 to -3, that's enough. Once we see a pattern here, we can get by with a lot fewer exponents, order pairs. But for the time being, let's use 3, 2, 1, 0, -1, -2, and -3. Let me extend these marks to make the table look better. You take the 3, you plug it in as the variable x, so you have 2 cubed. 2 times 2 times 2 is 8. So we just got the first order pair, 3, 8. Plug the 2 in up here for the x. We get 2 squared, which is 4. I agree. This is easy. 2 to the first power, 2. Now be careful. I think this was the first exponent rule that Tony wrote up here today. 2 to the 0 power, that's defined to equal 1. A non-zero base raised to the 0 power is defined to equal 1. Uh-oh, we're starting to plug in negative numbers. I need to change some of these colors. I'm using too much black ink here. It looks sort of dull. You take the negative 1, you plug it in there for x. 2 to the negative 1. What is that going to equal? Okay, using an exponent, it would be 0.5. Using it as, let's see, using it as just writing it as a rational number, remember, a negative 1, he said a to the negative n is 1 over a to the positive n. So, 2 to the negative 1, that's 1 over 2 to the positive 1, which is 1/2. But I bet that the 1/2, you got it using your calculator, didn't you? There's nothing wrong there. 2 raised to the negative 1. Sure enough, there it is. Is it 0.5 the same thing as 1/2? Plugging in a negative 2, we get a 2 to the negative 2. That's 1 over 2 to the positive 2. Once again, remember that definition of negative exponent. You move the thing down to the denominator, the sign of the exponent changes to positive. And what's that going to give us? 1/4. And if you punch it into your calculator, I bet you get the decimal equivalent. 2 raised to the, I forgot what I was punching in, negative 2. Sure enough, does give you that 1/4. And 2 to the negative 3, that's 1 over 2 cubed. And 2 cubed is 8, so 1/8. I'm noticing something. I'm noticing that as the x values get more negative, the y values, they're getting smaller and smaller, but they're still positive. Remember, I said a positive number to any power will always be positive. So at negative 1, we're down a half. We're up a half. But at negative 2, we're only up 1/4. Negative 3, we're up to 1/8. But realize you will never have an instance where the y value is 0 or negative. That will never happen. Because no matter what you plug in, whatever you plug in for x, the y value has to stay positive. It can't be 0, it can't be negative. Drawing an XY grid, one, two, drawing an XY grid. It starts, we have the order pair 3, 8, 3, 8. Then we have the order pair 2, 4, right 2, up 4. We have the order pair 1, 2, right 1, up 2. Then negative 1, so we're going left 1, up a half a unit. So here we are at negative 1. We're going up just 1/2 of a unit. At negative 2, we're only going up 1/4 of a unit. So that's not even up that high. At negative 3, we're only going to go up 1/8 of a unit. That's even closer to the x-axis. To the naked eye, it's looking like the thing's sitting on the x-axis. But remember we said there'll never be a y value equal to 0, so this graph will never actually touch that x-axis. We say that this graph is approaching the x-axis asymptotically. Likewise, the x-axis is a horizontal asymptote. asymptote. What you're going to want to remember about the graphs of exponential functions is that you should expect one side to be extremely flat, almost horizontal. You should expect the other side to be extremely steep, almost vertical. This thing is really starting to take off here. When x is 4, we'd be up at 16. When x is 5, we'd be up at 32. So as we move out to the right, one side's going to be very steep, the other side is very flat. If you remember that general shape, then you're not going to need all these ordered pairs. Now realize, it won't necessarily be the right side that's real steep. You could have the left side real steep, and that's the side pulling away from the x-axis. The right side could be real close to the x-axis, but you expect one side real steep, the other very flat, almost horizontal. So let's look at the function they want us to graph. They gave us one a moment ago. Okay, 6 to the x. Well, I'm not going to want to use so many ordered pairs here because 6 cubed is 216. I don't want to be counting up 216 units. Let me write the problem down. If we remember the general shape, you know something, where is it? Let's see. In general, we expect either the right side to be there. We're expecting two possibilities. That's not a very good picture at all. There, throw that down here. We expect it to be real steep on the right side and flat on the left, or it could be like that. But either way, for the graph of an exponential function, you expect a steep side and a flat side. So with that in mind, looking at number 13, they want us to graph y equals 6 to the x. I'm going to make a table of values. And I think I'm only going to use 3 x values. I know one side's got to be real steep, the other side has to be real flat, so the question is, which side is the steep side and which side is the flat side? I'm going to use 1, 0, and -1. I think from these 3 ordered pairs, I'll be able to figure out what the graph looks like. I'll start with 1. That says 6 to the first power. Oh, that's easy. That's just 6. So we have the ordered pair 1, 6. What happens when we plug in the 0? 6 to the 0 power is, it's that first rule we had, 1. And what about 6 to the -1? 6 to the -1, that becomes 1 over 6 to the positive 1, which is just 1/6. Keeping in mind the two general shapes, I think we can get a picture drawn just using these three ordered pairs. If you want to plot more, the reason I'm not going to use so many is if I use 2 for x, what would my y value be? 6 squared is 36. I don't want to count 36 units up. So here's my graph. Let me put a few tick marks. I'm putting these little marks down here below the x-axis, but is any of the graphs going to be down here? To be down here, it has to have negative y values. Are we going to get any negative y values? No, a positive number raised to any power must always be positive. So, right 1 up 6, left right 0 up 1, and left 1 up 1/6. I think I can tell right now which side's going to be the real steep side, the left side or the right side. The right side, that's the side that's pulling away from the x-axis. There's my graph. So it looks like that 2 to the x that we graphed earlier. So this is multiple choice. Let's pick out the correct response. Let's see. Oh, it's clear. I don't even think we have to blow any of these things up. Clearly not A. Clearly not B. There's only one that even looks slightly close. What is it? Which one did you say? C? I agree. Okay, number 14. Yeah. Same instructions, draw the graph. Instead of 6 to the x, it's 6 to the negative x. Realize, as long as the exponent contains a variable, then the expression is exponential. The exponent may be more than just a single letter x. But if your exponent contains a variable, you're looking at an exponential expression. So, this is going to be real similar to the one we just did, isn't it? We'll make our table of values. And once again, I think I'll only use 1, 0, and negative 1. I'm using 1, 0, and negative 1. Plugging in a 1. Hey, don't forget that black negative. We're going to get 6 to the negative 1 power. I think we just saw that, didn't we? 6 to the negative 1. What was that? 1 over 6? Yeah, I agree. Hey, what about plugging in the 0? Well, there's that exponent. The negative is 0. That's just 0. So 6 to the 0 is. Now plug in the negative 1. Combine that red negative 1 with that, that red negative with that black negative, and we're going to get 6 to the first power, so just 6. Keep in mind the two basic shapes. Either it's going to be rising or it's going to be falling. What do y'all think is going to happen here? Now I'm putting these little marks down here below the x-axis, just, I don't know, for balance or something, but will any of the graph be down here below the x-axis? No? So, we go right 1, up a 6. I think I can tell which side's going to be close to the x-axis. left, right, 0 up 1. And finally, left 1 up 6. Any questions there? So it's not A, it's not B. Oh, I think it is B, isn't it? What do y'all think? I think that's it, isn't it? It's clearly not C or D. So response B. Okay, and so let me, we talked about the definition of an exponential function. I never actually wrote it down, so maybe I should write out the definition. I said, what did I say? I said that the exponent contains the variable. I guess that's good enough. Yeah, the exponent is where the variable is. The base is a number. I guess I don't need to write a formal definition. But, okay, exponential equations.
We've solved linear equations this semester. We've solved quadratic equations. We've solved rational, radical equations.
And now we're going to solve exponential equations. We're going to solve them using two different methods. The first method that we're going to see is the same base method.
That's the only method we'll
see today. In a couple of assignments, we'll see a method. Suppose it's impossible to get the common base, then use logarithms, but that's not what we're going to be seeing today. This is the same base method. I'll say to solve an exponential equation, try to get the same base on both sides. Remember, the base is the thing that's written down low, the thing that's being raised to the power. Try to get the same base on both sides. That doesn't look like sides. On both sides. And the same base method says if b to the x is equal to b to the n, then if the bases are equal, the only way the left side can equal the right side is for the power to be equal. Then x must equal n. And if you think about it, it makes sense. This is a sensible statement. Let's consider the following question, or the following equation. 5 to the x is equal to 25.
Don't say 5. What number does x equal?
Realize the base here, on the left side, the base is 25.
No, it's 5.
I mean, the base on the left side is 5. Can we rewrite this number here as a power of 5? Sure, 25 is the same thing as 5 squared. If the bases are equal, the only way the left side can equal the right side is for the exponents to be equal. That x has to equal 2. The work here is going to be to get the same base on both sides. Notice we didn't start off with 5 to the power equals 5 to the power. We had to get a common base by rewriting 25 as 5 squared.
Sometimes students tell me, oh, I can do this one without, they just know 5 squared is 25. They don't need this step. Okay, but that's just what your brain is doing, even if you don't write that out. And it perfectly illustrates this statement up here. If b to the x equals b to the n, x equals n.
Okay, let's look at...
I think number 16 is a great first example. We can go back to 15.
I think...
You think 15 is better? Right?
No, I like 16.
Okay.
Let's see, this is number 16. Let me write it down. 2 to the 2x minus 3 is equal to 16. Okay. Solve the equation analytically. I guess that's the way of saying without using logarithms, but we haven't even introduced logarithms yet, so what other way would there be? On the left side, I generally start with the smallest integer base and try to get that same base on both sides. Well, 2 is a prime number. You're not going to write this 2 as anything other than 2. But 16, I think we can rewrite that as a power of 2. So the common base I'm going to work with is 2. 2 to what power gives us 16? What exponent would you need to put on that 2 to get 16? 4, I agree. 2 times 2 times 2 times 2 is 16. And then once you get here, it's getting the common base. Once you get to that point, you drop the base and set the exponents equal. If you have the same base on both sides, you can drop the base, set the exponents equal. I'd move that constant term over and combine it with the 4 to give me 2x equals 7. And then to give us 7 over 2. Go back to that number 15. It sort of reminds me of this thing up here. Okay, I'm going to write it right here. Number 15. 25 to the x is equal to 5. 25 to the x is equal to 5. Can you... Okay. Well, I don't know, 5 is the smaller base. You say, well, how is 5 a base? I don't see an exponent there. Sure, there's an exponent there. If you don't see an exponent, you can always assume there's a power of 1. I agree. So, 5 is a prime number. I'm not going to change it. But I know I can change 25 to 5 squared. So I'm going to change that 25 to 5 squared. And now we have a power raised to a power. Have you stated this as an exponent rule yet? No? Okay, then I need to remind y'all of something called the power rule of exponents. The power rule of exponents says if you have a power raised to a power, b to the m, like money, raised to the n, like Nancy. If you have a power raised to a power, you multiply to write it as a single power, m times n. And that's going to be a property we use quite a bit as we go through solving exponential equations. And there's even a rather bizarre power rule for logarithms that's based on this property here. Power raised to a power, 2 times x, that becomes 2x. And now we have the same base on both sides. So what do? If you have the same base on both sides, you drop the base, set the exponents equal. So that says 2x is equal to 1. As I said, the real work is just getting the common base on both sides. If 2x is equal to 1, what does x have to equal? I agree. To give us x equals 1/2. And okay, what's number 17?
I think it's just number 16.
Oh, I think 16 and 17 are almost the same, aren't they? So let's go on to
8.
Oh,
Yeah.
okay. Just switch over for this. Have you already? I know. Remember that an irrational number, a rational number, that's any number that can be written as the quotient of two integers, a fraction. Even like a integer 5 is rational because you can write 5 as 5 over 1. An irrational number is a non-repeating, so it's not like 0.33333 repeating, because that's the same as 1/3. It's a non-repeating, non-terminating decimal. I suppose the most famous example of an irrational number would be the ratio of the circumference of a circle to its diameter, which, since the numbers never repeat, the digits never repeat and they never terminate, to express the exact value we have to use a symbol. So what's that symbol in terms of circles? That's a famous irrational number. Looks like this. Maybe pi. But it turns out any square root that's not a perfect square is an irrational number. Something like the square root of 2 or the square root of 3. What about the square root of 4? Is that irrational? No, the square root of 4 is 2. That's a rational number. The square root of 5 would be irrational, and so on. There's another irrational number that is important for us. It's called the natural exponential, natural expo. The natural exponential. It's denoted using a lowercase letter e, and it's approximately 2.718.
28.
Ah.
28.
And okay, it's 2.718. 28. Well, we could just use my calculator. Well, it doesn't matter. It looks for a moment, when you look at the digits on a calculator, that it's starting to repeat the same digits, but then it stops.
That's
Okay.
18, 28, 18, 28, 1828.
Well, but it doesn't continue repeating.
46. You see, it stops repeating.
For our purposes, all you have to know with regards to natural exponentials is that e is irrational. You cannot write e as a power of anything other than e. So if you have an e as a base on one side, you better have an e on the other side, or you're not going to be able to get a common base. So with that in mind, number 18, e to the 13x minus 1 is equal to e to the 11th power, all raised to the x power. Well, it looks like I'm going to be using a common base of e. As I said, if you have an e on one side, you better have an e on the other side, because you're not going to write e as a power of anything other than e. So We have e to the 13x minus 1. Hey, we have a power raised to a power. What did I say we do with the power raised to a power? Multiply 11 times x is 11x.
Usually in algebra, to get rid of parentheses, you multiply. And that's what you do here, 11 times x.
Then we can drop the
Tim,
base.
Tim.
What?
Here, there. Okay, sorry.
Oh, well. You see, okay. I wrote the problem, and then 11 times x. Now we have the same base on both sides, so we drop the e, set the exponents equal, and as I said, the real job is just getting that common base, because once you get the common base, we've solved equations like this. 13x, what will I do with this 11x to move it over there? Subtract, so 13x minus 11x is 2x. Move that negative 1 over, that becomes a. So divide by 2 to give us x equals 1/2. Okay. Number 19.
It's a little similar.
All right, we'll do it anyway.
Okay, and this time as soon as you write it down, I'll put it in.
Okay, this is number 19. E to the 6x minus 1 is equal to e to the 4th raised to the x. So, if we're going to solve this equation using the same base method, we better have e's on both sides, and we do. So I'm going to write this one here without parentheses, e to the 4x. Remember, power to power you multiply. Drop the powers, set the exponents equal. So you have 6x minus 1 equals 4x. Minus the 4x to give me what here? 6x minus 4x is 2x, and here? And then divide by 2. Hey, this one also turns out to be 1/2. That doesn't mean every exponential equation containing an e is going to have an answer of 1/2. So that's certainly not the case. But number 20. Oh, this one looks good.
This one sets the pattern. There's no common base right off. You're going to have to figure it out.
We're going to have to figure out what the common base is going to be. Let me write the problem down. X plus 3. Normally, what I do, I start with the smaller base and I ask, okay, can I write the big number as a power of that small number? Well, 16 to the first power is 16. Well, what about 16 squared? I think that's going to be way too big. I think 16 times 16 is 256. Yeah, it's way too big. So we're going to have to change both sides. How can we rewrite 16 is something to a power and 64 is something to a power? I think of 4. That's what I'm thinking of. Can't we write 16 as 4 squared? What about 64? Can we write 64 as 4 to a power?
How many 4s can we multiply together to get 64?
I think 3 of them. 4 cubed is 64. So we can use a common base of 4.
And if you're wondering, wait a minute, what if that 16 were a 15, in which case it'd be impossible to get a common base?
That's when you use logarithms.
We'll
If you
answer that
can't get a common base, that's where logarithms come in, and that's several assignments away. But
well, we start logarithms on Monday.
Yeah, you're right. Okay. 16 is the same thing as 4 squared. 64 is the same thing as 4 cubed. And now we have powers raised to powers. So what do you do when you have a power raised to a power? I'm going to get rid of those parentheses. Power raised to power, we multiply. So here, notice we're taking the 2, and we have to multiply it by the 3x minus 3. So we're going to have to distribute. What's that going to give me as this exponent? 6x minus 6. And here we have power raised to a power. What's that going to give me? 3x plus 9. Now we have the same base on both sides. Without any parentheses, we can drop the base, set the exponents equal. 6x minus 6 equals 3x plus 9. I think I'd move this 3x over and combine it with that 6x by doing what? Subtracting 6x minus 3x gives me a 3x. And then we have a 9 plus 6, which gives me 15. Divide both sides by 3 for an answer of 15 divided by 3, I agree, is 5. Realize this is one of those rare instances where there are 2 options that you could use as a common base. It's not very common for this to happen, but we could have used 2. We could have used 2 as the base. 2 to the 4th power gives us 16. And is it 2 to the 6th power that gives us 64? So it's not very common when this happens, but it does occasionally happen. There are 2 different numbers that could have given you a common base. If you'd used 2 instead of 4, you still would have wound up with the answer of 5.
You'd have bigger numbers right up here.
Yes.
But you still get 5. Well, let's punch it in and make sure it's right. There. Oh, no.
Oh, did I miscopy the problem? 3x minus 3.
Oh, wow. Okay, it should have been an x plus 4.
Oh, well, this is just an example, okay? This is just an example.
So this is an example like number 20. Now he's going to really do number 20.
I'm really going to do number 20 now. I was just,
Okay, here.
Well, what is the problem? I forgot the
pull
problem.
it up. Here it is.
It's 16 to the 3x minus
How did
3 is equal to 64 to the x plus, it's x plus 4, isn't it?
X plus 4, not
And so we already said, switch it over.
Okay, so this is really his number 20.
Yeah, and you'll notice we'll still use that comment. Hey, I have a fun idea. Instead of using a base of 4, y'all want to use 2? Oh, you're right. Okay. Okay, so 4 squared and 4 cubed. We had a 3x minus 3 and an x plus 4. And then we're going to have power raised to power. So y'all call out what those exponents are going to be. Here. Okay, 6x minus 6. Here. Three times x is plus 3 times 4 is 12. And then what can I do? Okay, so we've dropped the base, set the exponents equal. Subtract 3x. 6x minus 3x gives me a 3x equals. What am I going to do with this minus 6 here? Move it over, so we'll have a 12 plus 6, which gives me, and then dividing by 3, we get x equals 6. 18 divided by 3 gives me a 6. So change that 5 to a 6. Number 21. Oh, what do I see there in those parentheses? What do I see as the bases that's appearing in the base? An e, then we need to write each power, each side with the base of e. Remember I said e is irrational. So let me write the problem down and let me make sure I did it. And this is not as bad as it might look at first glance. 1 over e to the negative x is equal to 1 over e to the 8 all raised to the x plus 7. Let me make sure I didn't miscopy this. There. We want to write both sides with just a e, not that 1 over. So it goes back to something we were doing at the beginning. Here when we had this on problems 5, let's look at 5 and 6. Look at 6. I seem to get the hang of it. If you had a 1 over and you wanted to write it without the 1 over, you make the exponent negative. Y'all remember that? Right back at the beginning of this ordeal that we call class? To get rid of the 1 over, make the exponent negative. Like right here, this 1, I'm going to do this side first. I'm going to write the 1 over e to the 8th as just e to the, what do I do to get rid of the 1 over? Negative 8, good. And then x plus 7. Now, at first glance over here, you might say, well, wait, there's not an exponent on the e. This is different from over here. But, as we said earlier, there's always an exponent. If you don't see one, just assume there's a 1. There's 1e here. So instead of writing 1 over e to the first, we're going to write e to the negative 1. Very good. Now we're ready to write it without the parentheses. So multiply negative 1 times negative x is just x. Over here, distributing the negative 8, what are we going to have? And is that a minus 56? Okay. Now, the bases are the same, so the exponents have to be the same. So I'm dropping the black e's, and we have something pretty easy to solve now. Let's see, what would we do? I'd move the x term over on the left side, to the left side. So x, is that going to be a plus 8x? So what do I have over here? 9x equals negative 56. Divide both sides by 9. And what are we getting for this? X equals, just negative 56 over 9, yeah. Yeah.
doesn't go evenly. So negative 56 over 9. Okay.
Any questions there? Generally, if you view an example, I think they use 1 over e as the base, okay? But my advice to you,
if there's an e in it anywhere, write it without that. Just write it with an e as the base.
and also my advice is don't use a fraction as a base,
Mm-hmm.
okay?
But theoretically, I could do problem 20. Problem 20,
Yeah,
we could do it with a fractional
It would
base.
certainly be a miss. Oh,
Okay,
okay, this is a good one.
let's see. So, we'd said previously, let me see, flip over here. If you have a 1 over and you need to get rid of it, make that exponent negative. But also, if we read this rule, if we look at it backwards, if you have a radical, a square root, or a cube root, or a fourth root, to write it without that, you use the fractional exponent. Let's see, so let's write down number, is it 22?
Yes.
Okay, so we have the square root of 2 raised to the x plus 7 power equals 4 to the x. Well, the common base, notice I'm not using lined paper today, but I'll go back to lined paper the next time. So it's sort of slanted. The common base will be a 2. And so
How can we rewrite the square root of 2 using an exponent without a radical?
we don't want that square root there.
2 to what power is the same thing as the square root? What exponent is the same thing as a square root? An exponent of 1/2. It'd be better if it weren't a 2 under that square root. If it were something other than 2.
But then it'd have to be a different number other than 4.
No, I know.
So I'm rewriting the square root with the red 1/2. And now, usually at this point, to get rid of the parentheses, we say, multiply or distribute.
Well,
But, wait, what have I done? I messed up right here. I forgot to rewrite the 4 as... How should I have rewritten the 4 to have a common base? Would it be 2 squared? Okay. You see, I'd written a 4 there rather than rewriting the 4 as 2 squared. Are y'all caught up with me? Yeah.
power raised to a power, what are you going to do on both sides?
Okay. We normally multiply those. Like over here, we distribute the negative 8. Over here, distribute the 3, distribute the 2. But for this one thing, where there's this fractional exponent, I think instead of multiplying them together, distributing, if you just write it like this, 1/2 times x plus 7 equals, now I'll multiply those and just say 2x. I think this is going to be an easier way of solving the equation than distributing the 1/2. Because I can get rid of this red 1/2 by multiplying both sides by a red 2, just to cancel that out.
And then on the left side, all you have to distribute. What have you got sitting in front of that x plus 7? Just
Yep.
a 1.
So just x plus 7 equals 4x. Oh, let me bring this low down. And how would y'all solve this thing for x? Yeah, good. Move that x over. So 4x minus 1x. That's going to give me a 3x on the right, a 7 on the left. Okay, divide both sides by 3 to get 7/3. That is right. Okay. So 7/3. Any questions there?
This is a common feature we're going to use with as we go through logarithms. When you see a radical, rewrite it using an exponent. Okay, so that's going to be popping up repeatedly as we go through the discussion on logarithms. I'll do this one.
Okay.
Okay. This is number 23. Let me write the problem down. We have the square root of 3 all to the x plus 9 power is equal to 81 to the x. Let me switch out. Let me make sure I don't miscopy the problem. There. Okay. 3 is a prime number. You're not going to change 3, but you know how to write the square root of 3 as an exponent. You know, writing the square root of 3 as an exponent requires using an exponent of 1/2. The square root of 3 is the same thing as 3 to the 1/2. So I have that x plus 9 on the outside. We've got to write 81 as 3 to the power. How can we write 81 as 3 to the power? 3 to what power gives you 81? If you're not sure, play around with that calculator. Well, 3 squared, we know 3 squared is 9. 3 cubed, 3 cubed is 27. I agree, it's 3 to the 4th power. 3 times 3 times 3 times 3 gives you an 81. So that would be a 3 to the 4th. 81 is the same thing as 3 to the 4th. The square root of 3 is the same thing as 3 to the 1/2. Power raised to power, so we. Power raised to power, so we. What do y'all think of the way? I would have never done this right here, canceling out the 2. I would have multiplied through that 1/2 and then had multiple fractions and had to multiply through by the 2 to get rid of the multiple fractions. I like the way he did this. I like the way he didn't distribute the 1/2 there. I'm going to do the same thing here. I'm going to leave it as 1/2 times x plus 9 is equal to, well, we better multiply these exponents. What's that going to give me? 4 times x is a 4x. And then we can multiply both sides. Once again, we have that denominator of 2. Let's cancel out the fraction. We'll multiply both sides by 2, just like we did in the previous problem.
This is a much better example than the previous one because it's you mentioned there were too many 2's floating around.
Yeah,
Okay.
This one is better. The 2's cancel. All you have left to distribute is 1 over the x plus 9. 1 times anything just stays as anything. So we have an x plus 9 is equal to, here on the right side, 4x times 2, 8x. I'd move that x over to the right. That'd be the easiest thing to do to give us 9 equals 8x minus 1x gives me 7x. Divide both sides by 7 to give us x equals 9 over 7. Now I've got to move up. There. Any questions? 9 over 7.
Oh, what did I do?
Huh? Oh my goodness.
No, I messed up. I put 97 up on top. 9 over 7. I should be more careful. Okay.
Any questions there? Hey, what did we not do? There's something we didn't do. Let's do it. Number 17, so we can say we did all problems in this assignment. I'll be glad to get my notebook back tomorrow for class. We were scanning the class notes, okay? That's why we're not using the Oh, this is going to be an easy one. This is similar to one we've already done. So we'll do this one and then be able to say we've done the whole assignment. Let me write it down. 2 to the 2x minus 7 is equal to 16. 2 to the 2x. This is number 17, not 16. It's 2 to the 2x minus 7 is equal to 16. Okay, switch over for me. Okay, what are we going to use as a common base? Oh, I think it's easier. I think something's already there. I don't think we're going to have to change both sides. What's this base here? 2. It's a prime number. We're not going to. That's not right to change 2. Oh, wait a minute. I think you were saying 4 because 16 is 2 to the 4th. I'm sorry. I didn't. Okay, you were jumping ahead of me. You were saying to rewrite 16 as 2 to the 4th power. I thought you were saying to change 2 as 4 to a power. I'm like, then we're going to pick up 4 to the 1/2. I don't want to do that. But 16 is the same thing as 2 to the 4th, and then what can we do? Drop the base, set the exponents equal. So we have 2x equals here. What are we going to do with that minus 7? Move it over, so we'll get a 4 plus 7 to give us 11, and then divide by 2 to give us x equals 11 over 2. Remember, sometimes you don't have to change both sides. Here we only had to change one side. The 16 we changed to a 2 to the 4th. Okay.
I know this was a lot. It was a long assignment, but it was a perfect example of the blended. You might be able to determine when
were we doing
the foundations work and when we were doing college algebra. So we had a lot of review built in there. But any questions? How about I stop the recording?